Okay. So anyhow, essentially, it would have been easier to see the share content. I realized that, but the exercise actually was just a blend, very similar to what we do in concrete. The only thing is with concrete, it has the two aggregates. For asphalt, typically you have three, most of the time, 3 or 4. And at times you may have more, but predominantly, depending on where you are and depending on your VMA requirements, a lot of agencies in the States get by with three aggregates. So it all varies, depends on the source that you're working from and what's available in that source, how the aggregate was processed. Okay. I haven't had a chance to look at some of the labs that were submitted. I believe for labs now, I've opened up the Dropbox to just more than one submission, because many times you guys make a correction and you want to submit another lab, and that's fine. And you do it by email, and that's okay too. But I believe I've opened it up such that you can have unlimited submissions for your lab prior to the deadline. And just let me know which is the final one, and I will just download and take the last one or your final one. So just double check to make sure it's working. I know I fixed that up quite some time ago. Okay, we're going to continue with the aggregates. I'm going to look at the lesson notes. It's very brief. We're looking more at physical properties of asphalt aggregate, gradations and all that. We understand it from the concrete, but we're looking at the physical properties essentially, and what properties we need for asphalt aggregates. Somewhat different than for concrete aggregates. I mean, we're still looking at abrasion resistance and so forth, but this has a big bearing on the performance of your hot mix asphalt. Let me see what I have here in my share content, and we'll go. This. It's not. Sorry, guys. Come on. Can't seem to find it. It's weird. Just give me a minute, guys. Here, I think I'm going to find it here somewhere. Oh, here we are. Okay. I want to get onto my bigger screen here for some reason. You guys can't see anything, can you?
We did see.
Yeah, you had it up.
I had it up. Okay, just do it again. I did have it up, didn't I? Well, you know what? Just have to go right back to where we were again. Apologize. It's got to be the weather, guys. Okay, now. What's happening this morning? Okay, yeah, see that okay?
Yep.
Good, okay. We're looking at aggregates, and I'm calling it Unit 2A. We had Unit 2 before in concrete, but A signifies that we're in asphalt, okay? So just get the chat going here so I can see if you guys have any questions. You can also blurt it out, that'll help. Okay, HMA, hot mix asphalt, you'll see that acronym used quite a bit. We usually have 90 to 95% by mass of aggregates in an asphalt mix. Typically, if you'll recall from last week, I had mentioned that in Winnipeg here, we're running about 5.2, 5.3% asphalt cement. And as such, if we look on a mass basis, okay, everything is a unit of 1. So if you got 5% asphalt, then you got 95% aggregate. It's got a total of 100, okay? So just the 2 ingredients. And you're going to have air voids, but air voids are a little function of the whole mix. So by volume, you're looking at 80 to 85%. It's by mass. I apologize, some of your may be highlighted, some may not. Highlight. Once you download it. The aggregates play a very important role. It's like concrete. If your aggregates aren't any good, if you don't have quality aggregates, your mix isn't going to be good. So that's key. Obviously, the asphalt cement has to perform and function as well, or else your whole mix isn't going to be a quality mix. Essentially, we can categorize our aggregates into 3 sizes, very similar to concrete. We have our coarse, which is essentially retained on the 4.75. We have our fine aggregate, which is passing 4.75. And we have sometimes they have additives or mineral fillers. And these are the real fines that pass the 0.075. Sometimes you have to add a little bit, and that's classified as mineral filler. At some plants, due to environmental issues, they have a bag house which catches a lot of the emissions from the kiln as the aggregates are being heated, wearing down, and the conveyor belts and so forth. But from the exhaust, they've got a bag house, essentially a great big vacuum, and it catches a lot of the dust. And they'll recycle that dust many times and use it as a mineral filler back into the mix if they need it. From an environmental point of view, when they're catching their dust or emissions from their plant, they can use that exhaust, those real fines. Sources of aggregates, obviously. You got to look at your source. Most suppliers here now have done petrographic analysis under pits to ensure that they have sound quality aggregate. And most of the aggregates used here, in fact, I don't know if we're using, we got recycled, but again, it's based on natural aggregates just being recycled. But you can have synthetic aggregates or aggregates that are produced artificially. For example, at the mines, when you have leftover slag, you can make slag cement. You can also have the slag aggregate that can be used in asphalt. So you have naturally occurring deposits in a pit or a quarry. You open up a quarry, you blast the bedrock, break it down to size, process it to gradings, to crushing and screening. We have naturally occurring aggregates, and we also have synthetic or artificially produced in the industry. We know that we have 3 types of rock. In geotechnical materials 1, I don't think you cover that, but in geotechnical fundamentals, of course, I teach for the structural group and also for the 2nd year environmental. We look at the geology. We look at the aspects of rock formation, soil formations. So we have igneous rocks, we have sedimentary rocks, we have metamorphic rocks. And depending on the source, depending on the material. All three can be used in asphalt. Some are better than others, but the sources of aggregate. So we use natural run deposits. And again, then we're going to look at quality. Now, suitability of an aggregate for use in construction. Your Learn may not have this highlighted, so go ahead and highlight it. These are essentially 8 key factors that we look at when we're looking for the suitability of aggregate. Obviously, we know particle size and grading is very important. Top size, maximum size has to be chosen based on the thickness of your pavement going down. If in Winnipeg here, we do a lot of thin lift asphalt overlays. In other words, we peel off what we have that's on the concrete. Okay, we fix up the joints, and then we put the asphalt back in. So we're limited, maybe 60 millimeters. And that's why the type 1A mix that we're looking at is nominal size of 16 millimeter because of the thickness. So you want to go about 3 to 4 times. The thickness should be no more than 3 to 4 times the maximum size of aggregate. Okay, so that's why maximum size is very important. Particle shape and surface texture. Round, smooth marbles, no good. We want cubical, okay? The width, the breadth, and the depth, almost the same. Ratios of 1 to 1 to 1. You don't want long slivers, elongated aggregate. You want cubical aggregate. But you want sharp, angular edges, and we'll look at that. And you want a rough texture. You don't want to have smooth. And you guys did crush counts last year with Natalie. Well, there's a specification if you look at City of Winnipeg, and most agencies have a crush count. They have a crush count specification, 2 fractured faces. Then they know they've got the crush. Abrasion resistance or the toughness. Many times you can look at a tough aggregate, okay? But sometimes the Los Angeles abrasion or the durability is off. And we'll look at a chart here right away. Affinity for water or asphalt cement. Okay? You want an aggregate that is just thriving and searching for asphalt to suck it up, not water. You don't want aggregates that are prone to water absorption because you're going to have stripping. Come to that later. So you want affinity for water or asphalt cement. Specific gravity, there's 3 types of specific gravity we look at. Just like there is with concrete aggregate. Okay, you've got the bulk specific gravity. You got the bulk specific gravity SSD. You got the effective specific gravity and the apparent. Okay, we don't look into SSD for asphalt because you don't want water in the pores. So essentially, we've got bulk specific gravity, we've got effective specific gravity, and we've got the apparent specific gravity. And we're going to look at these definitions. The pore structure, the porosity, the absorption. Like aggregates for concrete, you have to know the absorption because you know that you're going to lose some of that asphalt cement that you're putting in. It's going to be absorbed by the aggregate, and then you're only going to have an effective AC content, the one that coats the aggregates. And we want to make sure aggregates do not have deleterious substances. You know, cleanliness. We don't want soft and weak particles. For example, shale, cherts. In some aspects, they have certain properties, but not good for us, not for asphalt. Okay. So these are about 8 key factors. This is the flow chart, aggregates, where you can get them. Don't worry about it. This is a chart that just summarizes some of the engineering properties, and this was taken out of the Bureau of Public Roads way back in the 1950s, and they've sort of categorized mechanical strength, durability, chemical stability. And if you look at our igneous rocks here, for example, we have granites up around West Rock Lake, northwestern Ontario. We don't, I think the one, Gull Lake in Manitoba is a quarry that produces a fair amount of igneous rock. and granite being one of them. And you can see here that the mechanical strength is good, the durability is good, chemical stability is good, surface characteristics are good. But again, like any other rock, and if you look down this column, you can have undesirable material. So you got to be cognizant of that. And you can get a very good crush shape out of it, because basically it's all produced from bedrock. Some of your sedimentary, limestone and dolomites that we use here quite extensively. Mechanical strength is only fair, and durability is only fair. Chemically stable, however would you use it? Based on the parameters. These, again, are some of the rocks that we're familiar with. I've highlighted these, but don't worry about it. These you do not have to know. I've highlighted them just to show that these are the ones that we typically use here and locally. We have our granites, we have our basalts, we have our limestones and dolomite sedimentary rocks. The thing to consider here is interesting to note, when you have a hardness of 18 and you've got Los Angeles abrasion of 18. Now let's come down here where we're into our limestones. We have a toughness of 8, a hardness of 14, but look at our Los Angeles abrasion, went up way up to 26. So hardness is not necessarily a good indication of your abrasion. If you're familiar with an abrasion test, you just throw aggregate in a big drum and you throw heavy ball bearings, steel balls, about 1 inch to 2 in diameter. And you throw them in with the aggregate and you turn the drum 500 revolutions or 1,000 revolutions, depending on the test. And then you do a sieve after the fact, and you'll see the particles have worn down. So you're going to have a fair amount of loss for each sieve size. So what you're doing is you're breaking down larger size aggregates into smaller ones. And that's the Los Angeles abrasion. So if you look at granite, we know that it's one of the hardest, toughest rocks. Okay? But yet its abrasion resistance isn't that good. Why? Anybody got an idea? Anybody?
Is it because it's made up of a lot of smaller crystals and those crystals can break off fairly easily?
True, to a certain degree, but what did I mention? Where do you normally get your igneous rock or your granites? Let's call it granites. Are they naturally occurring in a pit, or do you have to crush them from bedrock?
Generally crush them from bedrock.
Right. So you're going to get sharp, angular aggregate, right? So if I throw that in a drum and add steel ball bearings, what's going to wear off first? Those sharp, angular edges. Some of them are even like really pointy. So I'm going to have a greater loss. Whereas if I have a cubical, maybe a pit run aggregate, there's some crush in it from the processing. Okay, I'm taking larger pit run cobbles and I'm crushing it down, say, so I get 100% passing my 16 millimeter. So they're not as, I've got my angular, I got my crush count, I met that. But they're not going to wear down as much as all the sharp edges on a crush aggregate. So a lot of people figure, oh, I'm going to use granite. My LA abrasion is going to pass. Not necessarily. So this is a good indication here. You've got a Los Angeles abrasion for your limestone, which occurs naturally. Where's Hill? I mean, you can have crushed limestone from Stonewall, yes. But the aggregates that are cobbles and bowls that occur naturally in the deep pits at Bird's Hill, they are somewhat angular and they become a little bit more angular when you crush them down to size, but they're not real sharp slivers granite. So something to keep in mind. Granite, yeah, it's a tough hardness, 18 versus 14. Okay, anyhow, just to kind of keep in mind how important aggregates are. Okay.
Hey, John.
Yes, sir.
For the quiz next week, is it 2 hours or 3 hours?
2 hours. Quizzes are
2
usually
hours?
2 hours. It's just a fun. Why have I got 3 hours written down there?
It says 2 hours, but then you have 9 to 12, so I was just verifying.
Oh, sorry about that. No, it's 2 hours. Sorry.
And then assignment 1 to 4 is good study material for that one?
Yes, we're gonna be covering asphalt cements, I believe, and aggregates, right?
Yeah.
Yeah.
It says unit
So-
1 and 2.
Yeah, units 1 and 2, yeah. And the aggregates are gonna pertain to, using the formula that we're gonna go over here shortly within the next half hour on the assignment. Remember, there's an assignment. Can't remember what number it is, but it's the one where you do the 3 aggregate blend using P is equal to AA plus BB plus CC and so forth.
I think that's assignment 2.
Okay, so we're gonna look at that one. We're gonna look at it hopefully in the last half hour here. And just so you guys, I don't know, how many of you guys have done the assignments? Do you find it all straightforward or are you guys all lost? For those of you,
Guidance wouldn't hurt, I don't think.
I'm sorry, what was that I was talking?
I said a little guidance wouldn't hurt, I don't think, just to clear stuff up.
Okay, good enough. Okay, fair enough. Any other thing about the quiz? Okay, gradations, we know. We've done enough gradations. We understand the importance of it. We understand how to read a gradation. We know if an aggregate is running coarse. We know if an aggregate is running fine. We also know we need well-graded material because if we don't have well-graded material, it's like trying to compact beach sand. You can't do it. Try and compact all one size of marbles. You can't do it. But if you've got large marbles, small marbles, you're going to fit them in. You're going to have better compaction. And with the asphalt, as you're compacting, as you're rolling, you want the aggregate interlock. You want the aggregates, and that's how asphalt works as compared to Portland cement. Remember Portland cement concrete? You want a coating around it, every individual aggregate. Yes, you need coating of asphalt cement around every aggregate, but it's the interlocking of the sharp angular edges and the rough texture that binds the cement to the aggregate. And again, this is the same as we talked. We have coarse aggregate, we have fine aggregate, we have filler. You know how to plot it. Okay. Resistance to abrasion, toughness. Aggregate's toughness is measured by its ability to resist abrasion and degradation. You have abrasion, obviously, from the processing of the aggregate. Excuse me, but you also have abrasion when you're compacting the hot mix and you're constructing the roadway. So you've got abrasion just from the compaction, from the wheel loads, and then you've got abrasion continuing from vehicular surface traffic. As the pavement is serving its needs year after year after year, you've got lots of wheel loads, you've got a lot of repetitive wheel loads, you're getting abrasion. So that's what we got to look at. We want an aggregate that's not going to wear down or degrade. And again, typically the alley abrasion machine, Los Angeles abrasion test, sometimes referred to as the Los Angeles battery test. Okay. Soundness. This is the aggregate's ability to resist deterioration. Okay, freezing and thawing, and wetting and drying. Okay, it wets, absorbs water, it dries out. Volume change, freezing and thawing. We know from temperatures. We have aggregates that are wet, they freeze, we get expansion. They thaw, they absorb, they freeze, we got expansion. So the soundness, and they usually use a test called the sulfate soundness test. And it's just a simulation, it's a lab test to determine the expansion, contraction of the aggregate. So we know that with volume change, you've got shrinkage, you've got expansion, you're going to have breakdown. The sulfate soundness test is commonly used to measure the asphalt's durability. You don't have to know how to do the soundness test, obviously. Come on. But you should know that it's the sulfate soundness test. They used to use magnesium sulfate, I think they use, and they used to have sodium sulfate, but I don't know which they use now. Okay, so we're looking at the physical characteristics of durability, abrasion resistance, cleanliness. We got to have clean aggregates also. As we clean or wash our aggregates for concrete, we also need it for asphalt. You could have dirty aggregate, which is going to impede the asphalt cement coating the aggregate, adhering to it. So you want to have clean, rough, textured aggregate. You also want to have very minimal amounts. None would be better, but that's not the real world, of deleterious material. These are materials that are like organics. chert, shales. Chert and shales are aggregates that have very low density. They're not very good. Okay, weak particles, we don't want those. Clay lumps. Sometimes you got clay balls or clay lumps in your aggregate. And many times if you wash it and you don't wash it well enough, those clay lumps don't break down. Because you know that when wet clay becomes hard, it's hard. It's got some pretty good dry strength. Any other coatings you don't want, that may impede the function of the asphalt cement to the aggregate. Let me look at surface properties, and this is the affinity for asphalt, and I had mentioned it before. Aggregates vary considerably in their affinity for asphalt. Stripping, okay? You're going to hear that term a lot if you work in the industry. Stripping is the separation of the asphalt film from the aggregate by the action of water. And that is quite common if you're using recycled asphalt as a replacement. So let's say you're going to have 70% virgin asphalt and you're going to add 30% of a previous pavement that you threw in with it, recycled asphalt pavements, wrap. You have to be really careful on those aggregates and their affinity for water. And lots of times you're going to get stripping, so you have to compensate for that. And many times they just use lime. We know lime absorbs water. We know that MI used to use lime stabilization in their subgrades way up until about the late 80s, early 90s. Our clay soils don't need it, but MI did it because they did it 30 years ago and they figured they still had to keep doing it. But anyhow, so lime will soak up water. It's a good way to dry stuff. If you add a little bit of lime into your mix, it hopefully will control stripping if your aggregates prone to stripping. It's the separation of the asphalt cement film coating from the aggregate through the action of water. Therefore, aggregates that have a high degree of resistance to stripping, presence of water, are usually more suitable for use. Obviously, you want one that will resist that action of water, separating the asphalt cement. Two terms, I've highlighted them because they do come up on quizzes. Hydrophilic, those are aggregates that just love water. They absorb water. Strong affinity for water, more so than asphalt cement. Hydrophobic, water hating. That's what you want. You want hydrophobic aggregates that have a high affinity for the binder. Stripping of the binder film from the aggregate through the action of water may make aggregates unsuitable for asphaltic concrete mixtures. Such materials are hydrophilic. Many of these materials can be used with the addition of a heat-stable additive that reduces the stripping action. There's commercial products out there, but the most common is lime. And there's actually a test on Astro. I tried to find an ASTM one. I didn't look very long, but there is one for ASTM. But we just know that there are tests that you can determine. Astro, because the Asphalt Institute is from the States, a lot of their procedures and test procedures are Astro because they were basically derived for pavements and airfields, whereas ASTM, also American, but it's used for engineering in general. So if you guys work with AMI, you'll notice that a lot of their specifications will spec Astro. Okay, and internal friction. Okay, we want to look at internal friction.
Hey, John,
Yes, sir.
that on page 4 for gradation, that Tyler standard, where is that from?
Oh, don't worry about it. Tyler was a manufacturer of sieves. It's the U.S. standard sieve size. I remember reading that and I was going to take it out, and I guess I didn't. Tyler is just a manufacturer, just like the Endicott manufactures sieves. Tyler manufactures, but it's the U.S. standard sieve series. You know, the number 4, the number 8, the number 16. If you remember last year in your lab, you'll see our sieves on the back hanging on the wall there. They're all numbered in the U.S. standard sieve size. Tyler is just a sieve manufacturer.
Oh, okay, thanks.
Yeah. Okay, good question. Internal friction. That's the key to the performance. That's what gives us our stability. Stability is a measure of strength. In concrete, we talk compression strength testing. In hot mix, we're talking stability. And we measure with stability that you're going to measure in your lab. You're also going to measure the flow or the deformation. But it's key. If you had aggregates that were round and smooth, you wouldn't have much stability. You'd have great flow. You wouldn't have any stability. Very important property because it resists the movement of aggregates past one another on their traffic flow. Internal friction, interlocks. So what are the key factors or the key factors that we look at that gives us that internal friction? Obviously, the particle surface and texture. Particle shape. Is it round? Sub-round? Subangular? Angular? Degradation, obviously, we have to have it. If you're not going to have a good, well-graded mix, you're not going to achieve compaction. You're not going to get those aggregates to move into one another. And void ratio, obviously, is going to be a function of how well we can compact it. So particle surface texture. Don't worry about this little sketch. It just kind of shows you how it works. The rough textured aggregates produce a higher degree of interparticle friction than smooth aggregates. I've mentioned that over and over. And this is kind of a common sense thing. You kind of know that. Okay? It is even more important when asphalt cement is added to the aggregates, because the asphalt cement tends to act as a lubricant agent of the aggregate contact points. It tells you kind of how it works here. Here you're going to have more surface area, right? We know we have more surface area on a crushed aggregate than we do smooth aggregate because we have the peaks and valleys that all takes into your surface area. Particle shape. Okay. Here you can look at various aggregates. You can have an aggregate that is sub-rounded, let's say, with a rough texture. You can have sub-rounded, smooth texture. You can have angular, smooth texture, somewhat, and you're going to have angular, rough texture. Okay, so there's 4 basic scenarios, and one of them comes up in a quiz, and you have to list them in order of suitability. And as you can see here, this isn't the ideal sketch, but you want things that have edges that are sharp and angular. Okay, there's angular. You can see these edges, they're crushed. Here you're getting into rounded. And you will have that. You will have, because nothing's, unless, like I say, if you're going to crush your aggregate at a bedrock, then every aggregate particle is a fragment of a crushing operation. You go into a pit and you open it up, you're going to have sands, you're going to have gravels, you're going to have cobbles, you may even have boulders. So depending again on what the pit has, you're going to take that aggregate and you're going to run it through some jaw crushers. And the fines are going to go through, the finer material is going to go through, and you're going to go through your jaw crusher. You might go through your cyclone crusher, impact crusher, and you're breaking it down. So those big cobbles and boulders are being crushed. So you're going to get some crushed, but you're also going to get some of the smaller aggregates that are more maybe subangular, formed by natural environmental factors. Particle gradation.
So out of all those, what would be the worst? Like, would it be the very round or rounded?
Round, smooth aggregates would be your worst. Sub-rounded tells you, okay, you probably had sub-rounded was probably angular at one time, but through the environmental forces, it wore down, either by water or whatever. A smooth rounded would be your worst. It's like having a marble. Okay, so a sub-rounded would be better than a rounded, obviously, because now sub-rounded means you're getting a little bit of edging, you're getting some edges.
But what about the very round and the rounded?
Well, the very round, again, would be the garbage.
Yeah.
You know, you got rounded, you got sub-rounded, you got very round. Obviously, very round is more circular, say, or rounded than a rounded.
Yeah.
Typically, they've gone a little bit to extremes here. You can, if you're going to classify aggregates, you can say rounded. If you've got a sub-rounded, already start looking at, going to have problems. Essentially want subangular or angular. Subangular still means it's classified as angular, but it's not as angular as an angular one. Okay, get it? It's kind of sub. It's in between. Void ratio, obviously, no different than again. If you're going to have a good distribution of all sizes, you're going to get the smaller particles filling in the voids. Okay, if you're going to have poor compaction, so low void ratio, high void ratio. These doesn't show up very good, but here you got a void. Okay, so again, if you have all one size aggregate, it's kind of hard. You can push it as far as it'll go, but after that, those voids are still there. And you're going to need that for asphalt. No, our VMA, voids and mineral aggregate. You got to have a certain percentage because you have to make room for the asphalt cement, and you have to make room to have some air voids. In an asphalt mix, we want about 3 to 5% air voids. Absorption, porosity. You're going to have some aggregate that may absorb a lot of asphalt cement. And a lot of suppliers don't like that because that's your most expensive part. You know, whether you're using 150, 200 pen grade or whatever, your asphalt cement is going to be expensive. If you have to use 6%, costs more. So you want to check your absorption. And also, as far as water, if you have aggregates that absorb a lot of water and your stockpiles and your bins are wet and you're batching asphalt, it's got to be that much longer in the dryer, in the kiln, as you're drying your aggregates. Because of our reduced content, we're not looking at the batch planting operation, which I typically do. We look at the batch plant, we look at the various aspects of batching, the sequence of batching. But anyways, aggregates are just thrown into a big, circular, long kiln that rotates. And there's a flame in there and it heats those agates. And it heats it, but it also dries them because you want your aggregates bone dry. It's like taking them out of an oven in the lab. You don't want any moisture in them. You want the asphalt to be absorbed. So you dry them out. If your aggregates are very, very wet and have high absorption rates, you got to dry them that much longer in your drum, in your kiln, as you're mixing asphalt. You got to use something to create a flame, whether you're using diesel fuel or whatever, or natural gas at the plant. That costs money. The more fuel you're burning to heat the aggregates to dry them out, the more costly your operation. So economics comes in. But absorption can also have a bearing on the quality of the asphalt, not only in the production. Porosity indicates the amount of water an aggregate can absorb. Remember your porosity formula last year from Geotechnical Materials 1. Porous aggregate absorbs asphalt cement. Thus, a lesser amount of free asphalt is available to act as a binder. So, two things. You don't want it to absorb water. Now, if it's also very absorptive to water, it'll be more so absorptive to the asphalt cement. And again, now you're using more asphalt cement, another cost factor that the suppliers don't like, because that's the most expensive part. A porous aggregate tends to make an asphalt bit dry or less cohesive. To compensate for the absorption, an extra amount of asphalt is added to the mix. Okay, there it is. Now you're using excess asphalt because you know you're going to lose it. It's not effective. We're going to have total binder content or total AC, if you want to call it, and you're going to have what's called effective. Effective is what's effective, what's not in the pores, what's coating the aggregate and giving you the adhesion. Yeah. Any questions so far? A little schematic here. If you looked at what's occurring in an asphalt hot mix sample, okay? So you can see we have net or effective asphalt. Net is the total. Sorry, is the effective. You got total. You lose some to absorption. You've got net or the effective. You got absorbed asphalt and you got air voids. And here you can see it. You've got an aggregate. RD, effective RD is relative density. It's the same as specific gravity, remember? Specific gravity and relative density are unitless. Density is grams per cubic centimeter or kilograms per cubic meter. So relative density is just, it's a density relative to something. It would cancel out. If you look at this a little closer on your own, you'll see that there's various situations that give you the various specific gravities. Here we got an aggregate volume. Then you got what's aggregate is effective volume. Water permeable porosity not filled with absorbed asphalt. We're going to look at that in our next slides. So just kind of keep this in mind. You got aggregates, and these aggregates, some are filled with water, the pores. Some of the pores are filled with asphalt cement, and some of the pores aren't filled at all, period. But that's going to change your volume. Remember? When you're calculating bulk specific gravity, oven drive, bulk specific gravity SSD, you're using different volumes. And you've got the coating of asphalt cement on the outside. Obviously, you're not going to have round aggregate, but it's just a schematic to show you. And then you want a certain amount of air voids. These are the air voids at 3 to 5% that we need. That allows for undue traffic. Specific gravity. Also called relative density, is defined as the mass or weight of a given material compared with the mass or weight equal volume of water at a given temperature. Okay, so it's going to be equal volume, and it's going to be the same temperature because volumes change with temperature. So that is essentially the generic definition for specific gravity or relative density. And the three we have are the bulk, effective, and the apparent. And again, we typically always talk specific gravities at 23 degrees Celsius. Remember, you calculate it back. We know that asphalt cement is light, but it's still heavier than water. If you took asphalt cement, it wouldn't float on the water. 1.03, 1.029, depending again on who the manufacturer is there, depending on the grade of the asphalt cement, but in general, they run around 1.03. So you know it's going to sink because it's slightly heavier than water. Okay. This is bulk specific gravity. Bulk. Okay. Total. It's the ratio of the mass of a given aggregate particle measured in air to the mass or weight, if you're in states, of water with an equal volume, including the pore spaces impermeable and permeable to water. It's the bulk volume. So here you can see the voids. So here now you're considering this total volume. So it's not only the volume of the inert aggregate, it's the volume of these air voids that are going to absorb or not absorb the asphalt. Just looked at my time here. I'm going to put a pause on the recording. I got to make a phone call here. I'm sorry, guys. I just realized that I'm going to be in about 5 minutes. I'm going to pause the recording. Read on to the specific gravities. I'll cover it, but read on to the next ones. The bulk, the effective, and whatever. Oh, 9:50. Okay. A little late on my phone call, but that'll be okay. So I'm going to pause the recording for a minute here. And when I come back, we'll put it back on, okay? And I'll take my sound off so we don't. Just give me a minute.
John, can you unmute yourself? I think you're mute now.
Okay, now quickly go back just to what I said. Sorry. Okay, we've got the bulk specific gravity. It includes the aggregate, the inert aggregate, plus the voids. The effective does not include the pores that do not absorb asphalt, impermeable to asphalt. Pores not filled with asphalt cement. And here you can see in the sketch, you got a surface void. It's filled with asphalt, or it's not filled. So you got the pores. So in other words, it does not include these pores. So your volume changes again, remember? This all has to do with the volume. An effective specific gravity can be obtained by approximately, if you know the apparent specific gravity, and you know the bulk specific gravity. Am I still on mute? Oh, I don't have my headset, that's all. Just hold on a minute.
No, we can hear you.
So if you know the bulk and the apparent, you can get a rough average. Okay. However, there's formulas for each one that we'll go in through on the next slide here shortly, and also through our lab. Okay, so we got the effective. And then we have what's called the apparent, and you remember that only includes the inert aggregate. It's the ratio of the mass of a given aggregate, equal volume. It excludes the void spaces, which become saturated with water, if you were doing an absorption test. So it's only the inert aggregate. Okay, it's only the inert aggregate. So that volume is going to be the smallest, right? So if that volume is the smallest, is your specific gravity going to be greater or less? Of all these three, bulk, effective, and apparent, which is the lower specific gravity, which is the one in the middle, and which is the one that is highest? My internet is slow for some reason, eh? Got cut again, eh? Son of a gun, what's happening with my, maybe weather? Who knows?
Well, we can hear you. The apparent is the lowest, effective is the middle, and then the bulk specific gravity would be the highest.
Okay, which is the, what order do you say? 1, 2, 3 in that order? As I've got
I
it
was kind of
listed?
thinking it's the other way around, isn't it? Because don't you have less volume, so it would make it more dense if you have the apparent?
Okay, so which is the last, which is the one in the middle, and which is the greatest?
Let's go 3, 2, 1.
3, 2, 1 is being your less?
Sure.
Sure that. Which is the smallest volume?
3.
So if you have a smaller volume, wouldn't you have a higher GSA or density?
Correct.
It's 3-2-1 in the highest.
3, 2, 1 in the highest. So you're saying the apparent specific gravity would be the highest?
Yes.
Well, I see now I've got a couple of options here. We're gonna, when we get into our lab, we'll go over a couple of things, but even prior to the lab on the next slide, you guys are gonna find out if you're right or wrong. And it's good to know because it could come up on a quiz. So some of you probably agree with 1, 2, 3. Some agree with 3, 2, 1. Maybe some go 2, 1, 3. Okay, just leave it for now. We'll come back. The extent of asphalt cement penetration into the aggregate's pore spaces is less than water absorption. Therefore, it would be incorrect to use either apparent specific gravity or bulk specific gravity when we're doing mass volume relationships, okay? Those of you that may have done the assignment on calculating hot mix air void analysis, and I'd like to go over a couple of those problems, and maybe later this afternoon I'll open up the WebEx again just to go over them. Some of you may have other commitments, but there's those of you that have done those calculations, either using the schematic or using the formula sheet, may have an understanding now. But if you haven't done an assignment on calculating mass volume relationships for analysis of asphalt, you're going to have problems on the quiz. Okay. If the apparent specific gravity is used, the asphalt cement is assumed to be absorbed by all of the water permeable pores. If the bulk specific gravity is used, the asphalt cement is assumed not to be absorbed by any of the water permeable pores. So neither cases are true. That's why we work with effective. The effective specific gravity is more appropriate to be used. However, if the asphalt absorption of the aggregate is known, then you can use the bulk specific gravity for your density calculations, if you know your absorption. And based on a lot of the problems that I've put out there, we can calculate asphalt absorption. Okay. So I want to switch to some slides here. They're in PDF. That's those red ones. I hope you guys don't print a lot of those. If you are, I'm going to have to change it because you're going to go through ink like crazy. Those red backgrounds and got other ones that have blue backgrounds totally. If you're ever going to print in color or even in grayscale, you're going to go through a lot of ink. So I want to switch those slides. I'm going to go through quickly on them because a lot of it's kind of repetition on this. But there's a couple of key points I want to get to because it gives us, again, we'll look at that formula where we're going to calculate blend using the formula instead of the Excel spreadsheet where you just put your formulas in and you do trial and error, okay? Just like your lab. Any questions so far on this? There's a lot of material here. I realize that, but I'm hoping you guys read up on that on your own. I'm just trying to stress the importance of these aggregates. Specific gravities will come into play once we do a lot of calculations. Okay. Everybody see this? Aggregate blending absorption in specific gravity by NCAT. Okay. This is what I meant. It's this came in from a PowerPoint, but I use PDF because I think sometimes PDF WebEx works better. Okay. Essentially, we're going to look at aggregate specific gravities, gradations, blending stockpiles, batching, and combined specific gravities. Batching is essentially taking your proportions of 4 aggregates, weighing out what you need, blending it all together, putting it in a pan or a bowl, heat up your asphalt cement, add it to it, and you're going to mix it up and you're going to do your asphalt mix design. You're going to pound your briquettes. Specific gravity, we've gone through this again. Here's the apparent mass of aggregates that are oven dry. Now, this isn't really a formula for specific gravity. This is a formula for apparent density. Volume of aggregate should always be multiplied by the density of water, right? But in metric, it's essentially the same thing. Because this is either 1,000, if you're looking at a cubic meter, or the density of water is 1 gram per cubic centimeter. So specific gravity is unitless. So if you took the volume of aggregate times the density of water, it gives you unitless. If you leave it this way, this is actually mass per volume, which is density. Okay, so this formula isn't technically right, but I think we understand it, right? So here it is, apparent specific gravity. Here's our bulk specific gravity, and this is how we determine it. It's the mass of aggregates that are oven dry plus the volume of the aggregate plus the surface voids. effective specific gravity. It's the dry mass divided by the effective volume. What's the effective volume? It's the volume of solid particles plus the volume of these surface voids not filled with asphalt. So it's these white ones. Okay? That's the effective specific gravity. Because it's going to have a bearing on our calculations. Water absorption, just an idea. SSD weight or mass minus the oven dry mass divided by the oven dry mass times 100 is water absorption. Typically, absorptions are always in percent, okay? So always multiply by 100 to get a percent. This tells you how to do the test. I'm not going to cover it. You did it last year with Natalie. Maybe not on aggregates, but we did it for concrete aggregates. So it's the same thing. Okay? These are just the procedures. Remember how we dried it in the towel? Couple calculation examples here. Fine aggregate, remember you pound it in the cone, lift the cone up. So the tests are the same. Specific gravity test is the same. Distribution of particles determined by sub-analysis. Types of mixes. Our mix that we're doing in the city of Winnipeg is obviously a well-graded. It's not open-graded, as you can see here. That would be a mastic mix. And it's not gap-graded. The bottom picture here you can see shows finer particles and intermediate particles are not in existence. A well-graded, you can see you got the larger particles with intermediate sizes in between, and you'll still have some air voids. Now this is super pave aggregate gradation, but it's just as important for Marshall. We're not designing by super pave. We should. We wouldn't have the time even if we have our practical labs to cover both Marshall and super pave. We're still in Marshall. City of Winnipeg's Marshall. MI's Marshall. Although MI now is finally doing a couple of super pave, but typically all over the States, all over Canada, the Marshall has gone to the wayside, and most people are designing by the super pave. MI was very reluctant to do it. They were trying to correlate for the last 10, 15 years, trying to correlate super pave with Marshall. You can't correlate it. It's either one or the other. But
What's the reason for their change?
Super pave takes into account your performance graded asphalt cements. Remember, we looked at it a little bit briefly where it looks into existing asphalt cements during the service life, whereas Marshall only tests in the barrel, if you want to call it, or in the tank asphalt cement when you're just adding it to the mix. They're not taking into consideration the asphalt cement during service life, which you have to design for. And essentially that's what they do. Plus it's a different way of compaction. Super pave, put it in a mold just like we do with Marshall, but with Marshall we put a hammer in it and we drop it, almost like a Proctor hammer, okay? Except it's a Marshall hammer, it's heavier. And you're compacting it in a mold by dropping a hammer, like a Proctor. Gyratory compactor is there's like a big knuckle or a fist, heavy weight that goes in the mold, and the mold rotates, kind of gyrates, so you get a kneading action. And that's how asphalt actually behaves in the field. It's not impact. You may have a little bit of impact when you're compacting asphalt, you're doing your breakdown rolling, but then you get the wobblies. Remember the pneumatic compactors? You might have seen those. That's the one that's loaded with ballast, and they may have 8 wheels in the back, 8 wheels in the front, and they wobble back almost like they're loose axles, but they're designed as a kneading action. Hey, you're manipulating asphalt. For the gyratory compactor, as part of the super pave program, tries to simulate the degree of compaction to match what's happening in the field. And there's a few other physical properties that you look at when you're designing. However, it's still based on air void analysis. You still need your VMAs, you still need your air voids, you still need your asphalt cement, okay? If you took a sieve analysis, okay, and you change the log scale on the bottom to 0.45 power, Okay, so now you get an arithmetic. And this would be 0.075, 0.3, 2.36. So here's your number 4 sieve. Okay? This scale now is not logarithmic. And if you took a line from here to 0, where your particle size and your percent passing, and you went right to your maximum size, drew a straight line, that would be your maximum density line. In other words, if your aggregate gradation fell right on that line, you'd have the densest mix possible. You don't want that. You would have no air voids. Your VMAs would change. Asphalt pavement wouldn't perform the way it should. But you're going to want a curve or blend to either go above or below it, but not through it. Depends again what your mixer is designing for. And we've got certain control points, if you want to call it. And this is what we're going to look at when we're doing that formula. P is equal to AA plus BB. We have the 4.75 control and 0.075. You may obviously have a nominal maximum size because you don't want oversized material in there changing your whole grading. So you set up a few control points. Okay? So don't worry about this curve. We're not going to be plotting anything like this on a raised to the 0.45 power. You usually take 4.75, raise it to the 0.45 power, and you find out what it is, and you plot it. Okay? So this scale just changes. It's not a logarithmic scale that we've been used to plotting gradations. Okay, we've done this again, super paved designations, 1995. Looking at a different top size mixes. Here's a 19 millimeter, 9.5, a little bit finer, and one in between. So this just gives you an idea with your maximum nominal size of mix and what you can expect your asphalt to look like. Okay? Believe it or not, you've got oils. Ooh, sorry, not oil. EC. Boy, I should be buying donuts for everybody for saying that, eh? Okay. Why do we blend aggregates? We want to get a desirable gradation. Okay. Single natural required material is usually not enough. You can't make it. And it's also economical. If we can combine natural products with processed materials, blend them in, it's cheaper instead of trying to crush everything. Plus, if you have too much crush, you're going to get problems with your mix. You may have a tender mix. How do we blend? Well, your lab last week was trial and error. You can use for 2 or 3 aggregate blends, you can use the chart that you guys worked with last year with Natalie. I believe she covered combining aggregates using your chart. We have coarse on one side, percent passing, and you got the other one, the other side, and you join your limits, okay? Or we can use a basic formula. And it's a starting point, and it's great for 3 aggregate blends. And that assignment that I've uploaded is a 3 aggregate blend. And here it is. Okay, we've got 3 aggregates, aggregate A, aggregate B, and aggregate C. That's noted by the uppercase letter. Okay, 16 millimeter crushed limestone, natural sand, and let's say VMA sand. Or you may have processed sand, the chips, 6 millimeter crush. You may have natural sand, which may have a fair amount of VMA sand in it on the bottom end. So here's 3 aggregates. Supposedly this works for 4, 5, but when you get into 4 or 5 aggregates, you now got to use, what's the term? You've got more than one unknown. So your math is a little bit more trickier. I haven't had time to play around with trying to do a 4 aggregate blend by calculation, but
Is that ambiguous?
not ambiguous. If you had 4 aggregates, you're going to have 2 unknown variables in your calculations. Remember, we know that
just a substitution then.
Yeah, it's there's a term for it. I can't use it. Tasha always uses it. Anyways, it'll come. You'll see when we get into this. So in this formula, we can see 3 things. We got lowercase a, lowercase b, and lowercase c. Well, P, first of all, is trying to determine what's the percent passing on any given size of the blended material. Okay, you got 4 aggregates. You blend them, you want a P, a blended percent passing 4.75, passing 2.36, passing 19 millimeter, whatever the case may be. P, percent of material passing a given size for the blended aggregate. ABC, it's the percent passing of each individual aggregate, okay? 16 millimeter crush, 6 millimeter chips, whatever. That is the percent passing any given sieve. And ABC is what proportions? Okay? Are you using 25, 25, 25, 25? Or are you using 50%, 25%, 12 and a half, 12 and a half? Okay, these are the percent. So here, if you're looking at the formula, I'm using a certain percent of A. I'm using a certain percent of B material. I'm using a certain percent of C material. Now, what should A, lowercase a, lowercase b, plus lowercase c equal in this equation? Okay.
1.
1, right, which is 100%, but in decimal notation, it would be 1. Okay, so we know that if we're blending 3 aggregates, A plus B plus C is going to equal 1. In your lab, you had A plus B plus C plus D. That's going to equal 1, or 100%. So when we look at a spreadsheet, we can then determine, okay, and then we're going to take it in our lab. We're going to look at your blend from last lab 6, whatever blend you got. You're going to use that blend, and you're going to figure out how much mass of each aggregate I need. And then you're going to mix it back together. You've done it theoretical by blending. Now you're going to take that theoretical blend, you're going to physically rip it apart, individual sizes, and put it back in. Thanks, Pavel. I'll have to keep that in mind. Okay. We want to reproduce the desired gradation for a mixed design. So what do we have to know? Well, you want to know each material, how much of each material are you using in the blend? You also have to know the individual percent of each material. You have to know their individual grading, so you can figure out how much of that aggregate of each size you're going to take. Instead of going through this, because we're running into time here, I'm going to pull up that assignment that I've uploaded that goes through a calculation of P. Okay, and I think you'll find it a little easier. And then that'll be easier to work out the individual masses that we're going to need for your lab. So this just gives you an example. Okay, percent retained, percent aggregate. Okay. And then there's a classroom problem here.
Hey, John.
Yes, sir.
Sorry, just about the lab we're handing in today. Is it possible to have them all in limits?
All in the limits?
Yeah.
Well, that's what you want. What do you mean by limits?
Yeah.
The grading limit?
Yeah, the City of Winnipeg grading limits.
Oh, right. But you want to try and shoot for the target one, as close to that target as you can, because it's no problem getting it in. That's not the problem in the combined grading. Problem is trying to get it close to that target, because that's going to affect your air void analysis.
And you're keeping those numbers to a whole number, right? So like, what if it's out on one, but it's in with the rounding?
Well,
does that count?
Yeah, that can happen. I mean, I always look at it in 1 decimal notation, and then when I'm calculating, then when I say this is my proportions, then I just give it to the nearest one.
So if it's out due to rounding, that means it's out of specs, and we have to state that in our report, or?
Yeah, because it should be in spec to the nearest whole number.
Okay, so rounding does count then.
Well, yeah, it does, but I mean, for analysis, just to see how much it is, because sometimes you might say I'm out 1 whole percent, and you're not. You might only be out 0.1.
Yeah.
So that gives you room, but say, okay, I got to look at it again.
Mm-hmm. And then for the report, it's just like the last one's the professional letter report. But what else is included?
Well, you want to just, well, obviously you're going to give me your,
The lab sheet.
yeah, the lab sheet and your graph.
Okay.
Okay.
Do we have to state our methodology on how we got to the numbers?
No, you can just say that you use an Excel spreadsheet and you're using various, what do you call it, trials to determine the ideal trial. The sieves were done in accordance with ASTM C-136. A sieve is a sieve is a sieve. It's got to pass. It's got to follow the sieve analysis procedure. Okay. ASTM C-136 and C-117 is the ASTM standards for doing sieve analysis. Okay. You guys didn't physically do it, but it would have been done. But the blending is not a CSA sieve test. It's an analysis to try and get a blending to meet the city would have expected. Okay? Does that make sense?
Yeah, thanks.
Okay. You're going to be calculating later on, we'll go through your combined specific gravity. We know that each aggregate on that spreadsheet, just like concrete aggregate, has an individual specific gravity, has an individual absorption. But if you're using 40% of aggregate A, you're going to use 40% of its specific gravity to get a blended specific gravity. And with this formula, you can see you've got three materials, percent of A plus percent of B plus percent of C. So this is essentially one, right? These percentages got a total 100. If you take the individual specific gravity of A, and you took the percent of A divided by specific gravity, plus percent B divided by specific gravity, percent C divided by the specific gravity, went through the calculations, you're going to get a blended specific gravity. Now, this specific gravity is the blended aggregate because it's the blended aggregate that's in the mix. Okay? Just gives you an example how to go through it. Apologize, I went through quickly. Let's just look at that. Before we take our break, let's just look at that assignment because we can take a break and then we'll get into the lab. Is that okay with everybody?
Yep.
Try and track down. Okay. Try and track down that assignment. Okay. Give me a minute here, guys. Got a couple here, so I'm going to put it on the screen. Just let me know if that's the one we're looking at. No, that's not the one. Come on. Here we are. Come on. Try and get the other one here. Okay. Come on. Okay, can everybody see this? This is the assignment. And you're gonna have one like this on a quiz. Now, sometimes on an exam, what I've done is we just calculate the percentages here that we need, gonna need for the course, for the fines and the VMA sand or whatever. I may give you just A, B, C. So A is the course, B is the fines, C is the VMA, and get the total blend. So here we have 3 individual gradations. And we want to blend. Now, when you're using this formula, here we're shooting for the middle of the grading limits. It could be a good starting point, and you can tweak it later. But we've got minimum, middle, and maximum. So our grading limits are 90 to 100, 75 to 95, 70 to 90. And here we're just using different sieve sizes. It's just an exercise in calculating. Doesn't matter what sieve size you use here. But here's our formula down here. P is equal to AA plus BB plus CC. We know that P is we're trying to determine percent passing an individual sieve on the blended gradation. Okay? A is the percent of the material passing a given sieve. So for example, A for the 4.75, A on the course aggregate is 19. B on the 4.75 is 83.2. C on the 4.75 is 92.3. We can look at the 2 millimeter and say uppercase A is 0.9, uppercase B is 62.2, and so forth. Okay? A, B, C, portions of individual aggregates. We know that A plus B plus C has to total 1. And we're going to start off. If we do substitutions, we can determine that A, percent of A material, in this case the course, is equal to the percent passing that sieve minus the B material minus the A. Okay? Everybody follow so far? Okay. Don't worry about this grading here right now, and right now don't worry about these percentages. I want to show you how we got it. Okay. We look at that 4.75 millimeter. Remember that one of the key sieves is to determine the coarse fraction versus the fine fraction on an asphalt mix. Just like we do at concrete. We know concrete we want 60-40. Here we may want 40-60. So we know that it's the 4.75. Sometimes it can be the 2. Okay, so what do we want to do? Let's look at the instructions here. Refer to the following tabulation of the gradation of 3 individual aggregates. Using the mathematical equation below, determine the proportion of each material required to produce a combined grading that would meet the grading limits. Okay. In this case, it says determine the combined grading. On an exam, I may not, depending on time, you may just solve those, but you don't necessarily need to give me that. Okay, depending on the time limit. But anyways, if you know these are easy to figure out because you've been doing that on your spreadsheets. Hint, to start, determine the approximate proportion of aggregate A. Okay, we're looking at A. To meet the midpoint or middle grading of a certain sieve that will give us a clean separation, okay, between the coarse and fine fractions. So if we look at A, what sieve size here gives us a clean separation? This is coarse, this is fine. Okay, you look at the percent passings, 100, 98, 84, 42, 19, 2. Okay, so which sieve in course A tells you This is the sieve that everything above it is coarse, everything below it is fine. It gives you a clean separation between the coarse and the fine. Is it not? Is it the 19?
4.75 or the 9.5?
4.75. Some people could say 2, but here, if you look at the 4.75, you got 2% passing. That means 98% is retained. That's right. That's a good answer. Okay, I mean, the difference here is only 1%, so it doesn't matter. This 4.75 is the screen that definitely tells you everything above it is coarse, everything below it is fine. It's a clean separation. It separates. Okay, so we're going to analyze that screen. That's the screen we're going to look at. Okay, so we look at 4.75. We know that the middle is 62.5% passing. That's the middle grading. So let's analyze the 4.75 first. If you go to this formula, A, and this is a typo error, that should be 62.5, not 62.6. But if we look at this formula, we're trying to figure out what percent of A coarse aggregate do we need. Well, P is the percent passing any sieve of the blended aggregate. Okay, we're trying to get 62.5. That's the percent of the blended aggregate that we're trying to meet. Okay, so 62.6 minus B. Okay, so we go to B, 4.75% passing. Remember B, 83.2. Divided by A, which again, okay, what's percent passing? 0.9. Minus B, 3 digits is 83.2. Okay, that's the percent passing. Don't worry about the negatives here because they cancel out. So in other words, we determined that we need 0.255 or 25.5% to start off with material A. Okay, now the key is how much B and C do we need? Okay, well, we also know that A plus B plus C is equal to 1. So the next sieve, or the next screen that's important, and it's going to control air voids and VMAs, is our 200.075. Okay, we got 3, middle is 5, upper is 7. So now we're going to look at 0.075. But before we do that, we can say that we know A plus B plus C is equal to 1. So then we know that B plus C is equal to 1 minus A. Okay? And we also know that B would be equal to 0.745 minus C. Okay? Because we know that if we subtract 0.255, we'll get 0.745. So we go back to this formula. P is equal to AA plus BB plus CC. We're looking at the 200 screen, 0.075. You know, P is the percent passing that we're trying to get. Go to the 200 and it's 5. Okay, it's the middle. So we know that 5 has got to equal A times A plus B times B plus C times C. We know that small a is we know that small a is 0.255. We just determined that up here, right? So what is the percent passing 0.075 for material A? 0.5. Okay, so it's 0.5 times 0.255 plus, we go to B, 5.3 times B. Well, we determined B here as equal to 0.745 minus C. So we plug that in, plus CC. There's 11.1% passing, 0.075 on material C, okay, times C. We don't know what C is. We're going to solve for it. Okay, so it's just straight math. We work these out. 5 is equal to 0.1275 plus 0.39485 minus 5.3C, because 5.3 times minus C This gives you minus 5.3 C plus 11.1 C. So now all our variables are C. We can solve for C. Go through the calculations, you solve for C. Well, we know C, straightforward. We now know B because we know B is 0.745 minus C.
So John,
Yes, sir.
on that first lab, would you classify the middle grading limits on this assignment as kind of like the specs from the city of Winnipeg and use those numbers?
Yeah, you could shoot instead of for the middle, you could shoot for the target,
Yeah.
you know. Or you could shoot for the middle and then that gives you an idea where you're at. Then you just tweak it.
Mm-hmm. So we can go back and do these calculations and find the exact amounts with,
Well,
but
you're
this is
working
only
with-
for
you're-
3, right?
Yeah, yeah. You could try and do for 4, but then you got to your math function increases now because you're gonna have 2 unknowns after, right?
Yeah. Okay.
That's why, I mean, this exercise is good because many times you are working with 3 aggregates only. Here in Manitoba, we're doing a lot of aggregates with 4. Like I said, I did one job we needed 5. But anyways, you could also take 2 aggregates and blend them. Okay, you got 4 aggregates. Take 2 aggregates, blend them as 1. And now you use A plus B plus C. But C is actually a blend of C and D. See if I can get that? So then you can use a chart. So you can blend 2 of the aggregates together first and then see how that works out. It's a lot of trial and error, but this formula is actually pretty quick. It gives you a good idea. So I went through this a little quicker, but the main thing is always refer to these calculations. Now I gave you the solution sheet. Now, once you've determined, okay, your percentages, 25.5% of A, 58.6% of B, 50. You could actually round these off to 26, 59, and equals 100. Or you can keep the 0.1% here. It's not going to change overall much, but here I went 25.5. So now it's 25.5% of 98.4 gives you 25, 25.5%, 42.3 gives you 11. These are just straight math functions, just like you did your lab and just like you did concrete. So your blend now is 25 plus 59. Now you can see we're not right exactly, but we're close. 96, we're in here instead of 97.5. 84 versus 85, 78 versus 80, 64 versus 62.5, 48 versus 45, 28 versus 25, 8 versus 7.5. I left these just to show that these are the middle. Okay? If we rounded this off to 8 and rounded off to 63, we're really close. And 6. Okay, so this is in the Asphalt Institute. If you looked at that textbook that I showed you, or if somebody got one from the library, all this is in there also. This essentially is going to be on a quiz for aggregates. Okay. Any questions on this, guys? This doesn't take long, even in a quiz. Once you start going through these calculations, you know what you're doing. You can rattle this off in 10 minutes. You're a fast writer, maybe even less.
Is there any other calculations for the quiz?
When we get into the hot mix asphalt, but not for this quiz. You'll have a blended gradation. You may have some calculations for pertaining to SIF. There's no other calculations for aggregates other than this that I can just try to think quickly now from memory. No. When we get into the void analysis, then you're using those other formula sheets. You're going to be calculating VMAs. You're going to be calculating asphalt absorption. You're going to be calculating the air voids. You're going to be calculating voids filled with asphalt. You're calculating combined specific gravities, and so forth. Combined specific gravity is pretty straightforward. Okay, just like when you look at that spreadsheet that you guys did, I may have even included it on Learn on yours, where you get the individual specific gravities, and your individual specific gravities are going to change based on the percent that you're using. So you blend the specific gravity, it's going to be different because it's a certain percent of the specific gravities of the individual aggregates that you're using. Okay. Clear as mud? Any questions, guys? Again, if you're going through these assignments and you're having problems, by all means, get in touch with me. Okay? I may not give you the answer, but I'm going to work with you for you to solve the answer. So we'll be well versed come quiz time. Okay. Same with the other assignment, there's a couple other assignments. They're calculating the void analysis. Assignment 3, I believe, or can't remember which one it is, but okay. We'll come up to that if there's questions. Again, I loaded up the solution sheet. Okay, let's take the lab shouldn't take too long, so we're still okay, I guess. We took this one a little longer, and then I had to take that phone call. But anyways, 10:43. 10 minutes good enough for a break? Grab a cup of coffee. So back here it's a 10:55. Is that okay?
Yeah, it should be good.
That's good.
Okay, so we'll see here 10:55. I'll just stop the recording and leave everything as is. Pause it, I should say. Let's stop it. Okay, let's take a little bit of a break. I need a cup of coffee here. Okay, we're back. Okay, Lab 7. I apologize, I haven't got Lab 7 loaded up on Learn. However, your Lab 6, you saw page 2 of Lab 6, which you shouldn't have had because it might have been a little confusing, but that's essential Lab 7, and I will upload it here after we're done. But we're going to review the second page, and I'm going to put it on just to show you, and then we'll switch to my other spreadsheet here. So give me a minute. Okay. Okay, you guys can see this. This is what's been uploaded and Learn, and this was your exercise, Lab 6. And page 2 is actually what we're working on, Lab 7. I shouldn't have given it to you. Apologize, because these numbers won't make any sense to you with these numbers being 0, 0, 0, 0. Okay, I'll go to a spreadsheet, and you can follow the spreadsheet. And it's going to be based on your sieve analysis. In other words, your blended sieve analysis, what you came up with for Lab 6 as far as your blend. So this is just going to be an example. My numbers are going to be different than yours, but it's the same analysis. Let me just go back.
I think it was only lab group 1 that had this extra page. It wasn't in lab group 2's.
Oh, is that right? Okay, good enough. So it might have confused somebody, or okay. Let's go to the Excel spreadsheet here. Okay. This is what we were looking at last week, okay? This is...
Are you going to record?
On the recording, okay. I'm going to record, sorry. Zoom, okay. We're up and running now. Thank you for the invite. I mean, the reminder, sorry. Okay. Spreadsheet here that you see is what you guys were looking at last week, or we were looking at last week to come up with our blend. 28, 9, 5, whatever you guys came up with, okay? So that's your Lab 6. Down here on the bottom is what we're calling Lab 7, mass proportions of individual fractions. We know that we need percentages of 16 millimeter crushed fine, natural fines, and VMA. So we said, yes, we're happy with it. That's going to be our mix design. Now we physically have to take the individual aggregates and separate them to various fractions. When we mean fractions, we mean passing one sieve, retain on another, passing one sieve, retain on another. Then we're physically going to weigh out individual amounts of each of those fractions for each of the four materials. And we blend it back. Okay. So we know that when we're doing a Marshall mix design, we need approximately 1,200 grams of dry aggregate, and then we're going to add AC to it, asphalt cement. And we know that gives us the proper thickness in the mold, proper mass. Excuse me, and that's part of the Marshall mix design. Now, when you're doing a Marshall mix design, sizes. So we're going to look at a fraction size. We're going to separate our aggregates, not for every sieve, but maybe 2-3 sieves combined. So the first fraction, depending on your grading, is passing 25 millimeters. We want to retain on the 19 millimeter. We're going to weigh out a certain amount of that aggregate. We're going to look at the aggregate that passes the 19 millimeter, but is retained on the 9.5. So in other words, it passes the 19, but it's retained on the 9.5. So it includes these sieves. Okay. Passes the 9.5 and retained on the 475. So what some people actually do is instead of doing percent passings, they actually do percent retains. It's doable. It's just the opposite. I find it just as easy to do it this way, and we'll have a look at it. Okay. Then we're going to look at the material passing the 475, retained 236. Okay. So we got passing, retained. Now, if I'm going to use 1,200 grams of aggregate, how much aggregate of A am I going to need? Well, my A tells me I need 28%, so 336. And if you look at my formula here, it's F8, 28% times 1,200. I'm going to use 9.5% of crushed fines, okay, which works out to 9.5% of 1,200 is 114. I'm going to need 690 grams of material from natural fines, and I'm going to need only 60 grams of the VMA sand, because I'm only using 5%. So if you total these, yes, sir.
Is it common to have such high natural fines, or does that just depend on the gradation you have with your sieve?
It's common. Typically, it's the VMA sand you have very little. It depends. Like this is an example I pulled from a few years back. You could have. There was one year I think we had a heck of a lot of VMA sand fines compared to natural fines. The trouble is if you use too much crushed fines, you're going to have a tender mix. You need some for stability. That's why in the industry they've gone to natural sand and manufactured sand. Okay, crushed fines are the 6 millimeter crushed limestone. It's produced when you're processing your coarse aggregate. And they found out that they need that for VMA and also make sure the mix is too tender if you have too much of it.
And with a tender mix, you mean like where you would leave tire imprints on a hot day or something like that?
Yes, and it wouldn't have much stability.
Okay.
Okay, yeah. It all depends on your design criteria. Like when you're designing for Winnipeg streets, we're using 75 blow Marshalls, really densifying it. I've done projects for Transport Canada for the runways in Winnipeg. They only use a 50 blow compaction, so the densities won't be as great. But again, they're looking at volume of traffic and the loads, the thickness of the mix too. So all this comes into consideration when you look at the fundamentals of asphalt design. We're not going to cover too much of that, just don't have the time. Anyway,
so it's okay for it to be tender if it's heavier loads, just not as frequent?
Well, no, the tender mix is going to be we say tender, it may not even compact well under the rollers. It fluffs.
Oh,
Okay, so it could be both. A tender mix could mean that it can't take a load or it's prone to temperature increases. Okay, like you were saying, if it's very, very hot, it's going to start to soften up quicker.
okay.
So it is natural. Here, you're going to have a lot of fines because remember, asphalt's the opposite of concrete. 30, you're going to have about 35, 40% coarse, more fines. So here you can see we're only running 28%, depending again on the grading of the course. Sorry, the grading of the course here. Okay. So yeah, it is quite natural to have up to 60%. You might have, depending on the grading on the VMA, may have 50-50 here. Okay, 25-25 or whatever the case may be. Yeah. So these are the fractions that you're physically going to separate each individual material. Okay. So let's get started. If we look at the 16 millimeter crushed limestone, crushed fines, natural fines, and the VMA sand, we have to determine what is the percent of the fraction retained. In other words, how much aggregate do we have retained on that fraction? Well, let's look at the 16. I'm not going to go through all of these. We'll do one example. Calculation for each one is the same using respective grading. So if we look at our 16 millimeter crushed limestone, we have a gradation here. Okay, 100%, 96, 60. So we're looking at our first one. What's the percent material retained on the 19 millimeter that passes the 25? We have none because it passes. We get 100% passing 19. So we have nothing sitting on the 19, right? We have nothing sitting on the 19. So 0%. Okay, let's look at the next one. We're looking at the fraction with the material passing the 19, retained 9.5. Okay, so passing 19, retained 9.5. We're looking at those. What's our percent retained on the 9.5?
So would that be 78 retained?
And how did you determine that?
Well, it's just 100 minus 22.
Perfect. Let's see if that's what we got. There it is. Okay, what's our percent passing 9.5, retained 475?
21.
This is okay. What's our percent passing 475 but retained 2.36?
0.
0. And percent passing 236? 1. Okay. Now that's
Would
the
that be
percent.
0.9 or would that be 1?
Oh, you can just use ones because you remember when you're weighing out this aggregate, you're trying to get 1200, and when you put everything together, you may still be 1202, 1203. But when you're actually ready to put the asphalt cement into it, you're going to do a final mass because it's going to be heated. You're going to heat that aggregate up again just before you put the hot AC to it, and you're going to get an exact mass. You're shooting for 1200. Okay, but maybe you get 1202. So then you're going to base AC, 5% AC based on 1202, not 1200. Okay? So this is again approximately 1200. Some people work with 1225. When you compact your briquettes, you have to have a certain thickness of the briquette. And we know from past experience that 1200 grams plus the AC could work up to 60 grams. So 1260, 1270, 1250 grams of hot mix will give you the briquette thickness that you want. And then you correct the stability of the briquette based on the thickness, and there's a range. And we'll look at that when we get into the actual mix design and calculation. So, you can use 0.9, but I just round these off to the nearest gram because it's irrelevant, okay? So this tells me that we need to go to this 16 millimeter material. And once we've separated that material in these fractions, you physically would sieve it. And like I said, when we have our practical lab in B109, we've got dust all over the place because crushed limestone, it's dry, lots of crusher dust in it. and it's just all over the place. So how much of each of these materials am I going to need? Okay, out of the crushed limestone, how much material of 9.5 do I need? This fraction. It all passed the 19. Okay, we got 78% of the material retained. So in other words, we want to get 78% of A. How much do we need?
If I had to guess, it's gonna be 262.
262. You're guessing, or how did you figure that out? You're amazing.
Well, that's the calculator. It's not me. But that's
Oh, yeah,
0.78
but the calculator
times the
will only give you
total
the
amount of
answer
mass
of what
is
you key
16
in.
mil.
Sorry, I was talking at the same time, being a smart aleck. That's fun.
0.78 times 336 grams. Because that's their total mass for that aggregate. So if we have 78,
Perfect. Exactly. You got her. Okay, this one works out to what? 0.21 times 336. There it is up there. I mean, you can physically just do it on a calculator. You need a spreadsheet. This is obviously going to be 0, right? And this is obviously going to be 1. 3, I should say, not 1. We total that, what do we get? 336. You do the same here. Same here. Now, these are my numbers based on this grading, and if you look at this grading, it's just anything. We're actually at a, here, on one of them, we're almost out of spec. Okay. Before I would have finalized this, if I was working with this, I would make sure I'm trying to hit these as much as possible. But this is just an example. You can see here, we're way out, better not, from my target. But in
So
your,
are you supposed to show that to 1 decimal place?
where are you referring to down here?
The total percent in the green.
Oh, yeah, you can do the 1%. It works out the same thing. I just did mine in 0.1, but you show it to 1%. This is your total blend. This is what you're going to compare against here, right?
Yeah. No, I was just asking because that was my question previous, right? On the 99 to 100, it wasn't, with rounding, it was 99, but otherwise it was 98 point something.
Yeah. Well, you do your best, and then you would show that it's being out. It's out. That's the best you can do.
Okay.
That's the best you can do. Okay. So these here are all pretty.
I think is 0.1%, right? I mean, everything's
What was
1% except for the 200. Or the
Uh,
75 micron.
75 microns is the 200.
Yeah. I think that one's
Yeah.
supposed to be 0.1, isn't it?
I'm not following. Okay, I missed a question. Sorry, start again.
No, yeah. Well, it's, I think based on the sieve analysis standards, it's all to 0.1 except for the 200 sieve.
Oh,
which
right.
is
Yeah, if it's less than
round to
10%.
the nearest 0.1.
Yeah. You got it. No, that's right. If percent passing 0.075 is less than 10, you show it to 0.1%. Everything else is 1%. Now, if your percent passing 0.075 is 15.2, you would report it as 15. Okay? And that's only applicable to the percent passing 200. I think I'm going to hold that. Is that Kelly?
Oh, sorry, I didn't mute myself.
No, that's fine. Okay. So I just went in. Now, these numbers here, again, like if you go to each one and you figure out percent retained. So some people, some designers, instead of using percent passing, they'll put up here percent retained, so they don't have to do that calculation. But it's pretty straightforward, 22 minus 1 is 21, 96 minus 60 is 36. So now when you're in B109, you would have actually, and then we'd need 4 samples. Okay, we'd want for 3 samples. Typically, you should do 3 briquettes for every AC content plus 1 for maximum theoretical specific gravity. But we've cut down our lab because of time in car C and in B109 because we compact in car C because we got the fume hoods and everything else. So now you would weigh out 262 grams, put it in a bag. Weigh out 262 grams, put it in another bag. You'd weigh out 262 grams, put it in a third bag. You'd weigh out 262 grams, put it in a fourth bag. Then you'd go and you'd weigh out 71 grams, put it in that first bag. 71 grams in the second bag, 71 grams in the third bag. Because you need 4 samples to mix up 4 hot mix briquettes. So there's a fair amount of grading and mixing and weighing that has to be done. And then obviously there wouldn't be anything there. Weigh out 3 grams, put it in bag 1, bag 2, bag 3, bag 4. Then when you weigh these out, you'd weigh out 16 grams, put it in bag 1 with this 71, because you want to make up 1,200 grams physically with these masses. Okay. Now, if you look at all these, they should total. Shooting for. And again, if you total these, they should total 1,200. So your lab basically is whatever blend you came up with. I haven't looked at all your labs. If you've got a copy of it, you can just spit it to me. And then your next lab next week is give me these numbers. Now, I'm going to try and intercept if I see that these that you have are way out from the target. Okay. These numbers are going to be, I'm going to try and see, but you shouldn't be too far out. You should be getting these as close as possible. And you're not going to get them exact. It's impossible. I mean,
So
I
what's
could have
the
done it in such a way
possible?
that would have. But these are
Like, let's
actually
say I'm
numbers.
4
Sorry,
or
go
5
ahead.
grams out. Let's say I'm 4 grams out, or 4% out. Is that close enough? You know,
Not really.
no. Oh,
But
well,
maybe,
just curious, because like if it, let's say I've got 56 on one and I'm bang on near 54, but then the one on top I'm at 67 instead of 63, and then the next one I'm at 82. But if I change things, then it could, go further out, kind of thing.
okay.
But
What I'm going to mention to you guys, no color. 0.3 is a critical sieve to give us a hump. So when I look at these, obviously I'm concerned about the 5.4. Okay, percent passing 0.75. I'm obviously concerned for 7.5. And the 0.3, okay, we found out that if you went right down the middle here, what would the middle be between 5 and 28? Okay, about 11. Okay, difference there is 23. Sorry, is about 16. So we want to get that hump. We want to be a little finer. So I would try and get these as exact as possible. If 5 to 28 is 23, half of 23 is 11 and a half. So 16 and a half would be right down the middle of the pipe. So if you went to 18, 19, 20% even, would be okay, because it's a 0.3. It's one of the critical sieves. And again, you guys aren't going to know that, and it's unfortunate because you haven't been in the industry. And that's why we come up with an 18 year. That's why we're not shooting for down the middle. We want to be a little finer there. So if you're close to 18, all the better. These can be out a little bit more then. Not a lot, but so these are the ones I would shoot for that are critical. 475, 075, 0.3. I've had talk with Hermie Manilow from Manilow Consulting and other people in the industry. This is a ridiculous spec that City of Winnipeg has come up with for their 1A. If you look at it, we put 100 in here, but their spec for a type 1A is 99 to 100% passing the 16 millimeter, right? But they do not tell you what the maximum aggregate size should be. Is it 20? Is it 25? What is the maximum sieve that 100% must pass through? They don't tell you on there. If you look at that 1A grading charts, they don't tell you. They tell you that you can have 99% passing 16. That means you can have 1% oversize. But when you read definitions, they usually tell you that maximum, not the maximum size is usually the next sieve above the nominal. So say you want to pick type 1A, 16 millimeter sieves got to be nominal because you're allowed 1% oversize. But they should still specify that they want 100% passing 3/4, or 19. Because if they don't, you could have a 37.5 millimeter aggregate in there. Doesn't tell you that it has to, so they should have said, okay, I want 100% passing 19 millimeter or 25, whatever, but they don't. And they don't give you a limit here for 12.5. You don't always need it, but it would help. They don't. Where they got that sieve from, guys, I don't know. You read a lot of the mixes in the States and in Canada, usually it's a 19 millimeter, 100% passing 19 millimeter. That's the maximum size. Then, okay, 99 to 100, and even 99, go to 95. Typically, oversized is you're allowed up to 5%. Why are they restricting it to 1%? What's that do? I don't know. City
I guess they're
workers are
pretty
pretty
much
good,
saying
guys.
they only want one rock in there. Kind of thing.
Essentially, yeah. And you know what may have happened? Good point there. What may have happened is maybe when the contractor is sieving, and if you've ever worked on a crushing and screening plant, sometimes those things bounce. And you can have aggregate bouncing out and falling through, an oversized one. So maybe when they've been doing sieve analysis, they found out that, oh, we've always got 1 or 2 stones oversized. So let's put that into the spec. I don't know. I honestly don't know how they came up with that one. Typically, you look at the Asheville Institute or a lot of the other testing specifications across the States and in Canada, and it's usually 19 millimeter top size maximum. And then 95 to 100 passing the 16 or the 12.5, whatever. So it tells you you got 5% oversize allowed, or you can have it all passing, 95 to 100, whatever. But, it's the same thing as MI did one time. Their concrete strengths for their when they're doing highways is phenomenal. It's way too brittle. And what their reasoning was that when they used to do concrete testing, they would find out that they would always get 7 to 8 MPa greater at 28 days in their mix design. So they said, well, in their infinite wisdom, they said, well, if we're getting 7% greater, let's just specify that much greater. So let's say instead of having a 32 MPa mix or 35, they said, let's go for 42. Well, again, remember what we said? If you're designing for a 42 MPa mix, you got to have that standard deviation. So you're going to be probably designing for 46 or 47. So now they're getting higher again. They're saying, wow, our concrete is way too brittle. Well, yeah. Why did you increase the strength? They didn't understand that from a design point of view, you got to have that cushion, a 5, 6, 7 MPa. You're going to fail somewhere along the line, 1%, 99% of the time you're going to make it. So they just kind of shot themselves in the foot. They created their own problem by making that concrete way too brittle. Okay, the ductility was way down. I mean, the higher the strength of the concrete, the less elongation you're going to have. Your stress strain curve is going to be way out. Anyhow, getting off the point here. Any questions on figuring out these percentages here? And the covering letter here is going to be very brief. You're going to say that based on the blended gradation previously determined, and you can show that to me for lab 7. You can do whatever spreadsheet here you want. I'm finding that a lot of times people are copying these as gospel. And it's the same thing as notes when you're studying for a quiz. And one question I noticed that a few people in the last quiz, the midterm, that I'm just about finished marking, will be posting. And one question about why do we water or moisten the granular base just before or immediately before we're paving? And so many people say 2 reasons, and I only gave one mark. And they say, for compaction purposes and to prevent the base from sucking the water out of the concrete, which is the right answer. Because I said immediately before, if you're paving, compaction's been approved. You've set your string line out, you've done probably a week's work before you're even ready to pave. So then they're paving a week after compaction's been approved. Why then are you just spraying the grade? You're not doing any more compaction. I only gave you half a mark. Because that's what the slide said. You typically use water to improve compaction, and then you use water before placing the concrete. Gotta read the question, guys. Gotta read the question. It said immediately before placing concrete. Has nothing to do with compaction. Compaction's already been approved. Yeah, you use water for compaction, but that could have been done a week ahead of time. Okay, so be careful when you're straight jobbing spreadsheets. Same thing can happen. Okay, any questions? So those that just said to prevent moisture from being drawn out of the concrete got 1 mark. Those that included both got half a mark. Okay, if there's no other questions and the lab is done, this lab is fairly straightforward. Just give a brief covering letter, a paragraph or two saying that these numbers that you present, and then show me in a spreadsheet or on an attachment or summarize it in whatever way you want that I can read. I can check to see if your numbers jive with your blend and these percentages. Okay. Any questions so far? No? About a half hour over what we normally should be at, but anyways. Okay. If you have any questions pertaining to these calculations, again, let me know. No questions? Well, okay. So this
Actually,
exercise.
I've got a question.
Yeah, go ahead.
So if we're not supposed to copy paste, what is the information that you need us to have on there? Like, do you like
Well,
is there an
no, set up.
we can read?
You can set up a spreadsheet. Okay, if you're going to cut and paste, I mean, I can't stop you, but if you're going to set up a spreadsheet, be careful because sometimes I give you numbers on an example, and it's very easy to use those numbers by accident in your calculations. I've done it, and I know it can happen.
So if
You
we
can
use
set it up in
your
you can set
spreadsheet,
it up in whatever fashion you want. You don't have to be as, I use these headings. You can use different headings as long as they make sense. What I'm trying to get you guys to do is also, and I know this isn't part of computer applications, but I know some people aren't well versed in Excel. And if you're not, then you can tabulate this freehand on a paper or type it out. You don't have to use an Excel spreadsheet. You can set up columns. Okay, that's what I'm saying. You can type these out in Word if you have to. You don't have to use an Excel spreadsheet. But you want to give me, I want to see some kind of a summary so I can follow it. It's got to be neat. Okay. So I've used an Excel here, but you can put this out in a Word document with a table attached, which is a spreadsheet eventually, but it's in Word. It's not Excel. So you don't have to use Excel. But you may be just very comfortable using these and putting in with a calculator after you calculate it. Any questions?
yeah. Anyway, because the point what I'm getting at is for a lot of us is the first time we see any of this. So we're going to assume that what you are doing is right, and we should be doing that because we don't know necessarily what we should be reporting. That's what I was getting at, really.
Yeah. Well, I could have done this very just on a piece of paper, if you want. I don't know if you would have appreciated that. I would have just written this out in my Scratchy and said, okay, this is 0, this is 28. I mean, doable. I don't mind you guys looking at a spreadsheet and using it as a basis. Okay. I just found in the past, and it's not necessarily this group, but I found in the past that people sometimes will even ask me to put up the Excel spreadsheet, not a PDF, so they don't have to calculate anything. They want me to give the formulas. That's not my intent. If that's the case, but then I'm doing your work for you. Okay? So that's why on lab 6, I gave you these numbers, obviously. Sorry. Okay. You had to calculate these. This. I think I even gave you this, did I not? Yeah. If I didn't give you this, okay, I didn't give you this. Could you guys, if I just wrote it on a piece of paper, this is the percent passing, percent passing, percent passing, percent passing. These are the sieves. Could you have guys developed this yourself? Sure you
Only
could.
if you told us the information you needed us to present.
Okay, well, I got to give you the gradation. These would be typically things you would determine in a physical lab. These are actual numbers that were determined by students in third year municipal, just like you guys. Okay, I'm using back 5, 6 years, whatever. So these were physically determined sieves, sieve analysis, just like Natalie had you guys doing last year, sieving A base or whatever. And I do a spreadsheet for demonstration purposes, but whether you're going these in reverse, VMA stand first, whatever order, doesn't matter. Okay. If I gave you these on a piece of paper, just in a column, in Word, said, okay, here's the sieve, these are the individual percent passing. I'm sure you guys could have done that.
Yeah, what I meant more was you give us your 4 materials, but you tell us you want us to give you individual percent passings for each material. You want us to present the total blend of each one, and you want us to write down that, and you want us to give us the asphalt, the absorption, the bulk, density, and so forth. You know, just say I want this, 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 and this in your report. Write it. That would be very handy.
Yeah. Okay. Fair enough. So for this one here, I want to know these numbers for each sieve. Oh, sorry, for each sieve and for each material, okay? And how you got them. You can use a spreadsheet, I mean, but you know, all I'm just getting at is devise your own spreadsheet, that's all, okay? Maybe you guys might not like this. Maybe there's better ones, I don't know. This is something that works for me, it may not work for everybody. What I'm getting at is if I see a report and I can understand it and it's clear, it's legible. And again, if my mother could sit down and understand it, then you've done your job. Or my wife or my accountant or somebody, okay? I can read this spreadsheet, exactly what's going on here. But like I say, maybe your format's a little different, but as long as I can understand it, and I know that your numbers are correct because you went through, you know, the proper calculations. Okay? Anything else? Good. Well, like I say, we're done then, and if there's any other questions that you may have throughout the week, let me know. So, I apologize again. I don't know what happened with the recording last week. I'm going to make sure I'm careful on this one. Maybe I hit the recording or stopped it too early or something, but for some reason it went to a WebEx format instead of. It's the first time it's ever happened to me, so I think we're over the hump. Okay, if you guys are done, I'm done. Good week. Hopefully it's going to warm up some and the snow will melt. Okay, guys. Thank you. And later. Okay, goodbye.